Greetings class, Professor Steve here, and welcome to our wave lecture. Okay, so waves are sort of on the smallest scale of ocean circulation in terms of how the ocean moves or how any water on Earth moves. And they behave a little bit differently. They don't, for the most part, they sort of, if you take a large section of ocean and look at all the waves on it, they are affected by Coriolis, but individual waves on the whole are not large enough, or not a large enough phenomenon to be affected by Coriolis. So the main questions that we're going to answer for this lecture are why does the ocean have waves, or why does any body of water have waves? What are the different parts of the wave? And then really the last two questions are the big ones, and that's how does the water move? How does the water behave, and why does it behave that way? So the definition of a wave is displacement of energy caused by a disturbing force. Okay, so the energy disturbing force, that's really the key term here. So some force, outside force, disturbs the water and transfers its energy to the water. A more basic definition of a wave really can travel over or be used to describe any type of energy movement, right? So rhythmic movement that carries energy. And most of us have seen mathematical descriptions of these kinds of things in one way or another. But obviously in the ocean, the waves move through the seawater. Okay, so the majority of waves, okay, and so a wave is a much more intuitive thing to most of us. We're all familiar with waves. You can stand on the coast or on a boat and watch the waves roll by, or at least what looks like waves rolling by. And you also usually are feeling at that very moment what's causing the wave, and that is the wind. The wind causes waves, just like it causes the larger portions of the surface ocean circulation, the currents and the gears, but just on a much more localized scale. So the wind moves past the water, just as we described in the other lectures, and the friction from that interface, from the the air-water interface, that friction causes the energy from the wind to transfer to the water. And then very low wind, low amount of air movement causes not very much wave, but if the wind starts to pick up, that energy gets strong enough, we start to pile up water, enough energy starts to pile up the water, and we get a wave to form. Okay, so the parts of the wave, most of us should be familiar with this in one form or another, should have seen this sometime in our education. But one full wave is from a crest to a crest, the center of a crest to the center of a crest, or you could say from the center of a trough to the center of a trough, right? So that we call that the wavelength. Lowest part of the wave is called the trough. The highest part of the wave is called the crest, and the wave height is the measurement from the bottom of a trough to the top of a crest. So here we are seeing it again. Here's the definition of all those things. Right, wavelength is from equal parts from an equal part to an equal part as a measurement of the wavelength. So the center of a wave, or the center of the crest, or the center of the trough to that next equal part is the wavelength. The wave height is the measurement from the top to the trough, again, and the amplitude, when we say amplitude, which is a word we won't use very much, is half the measurement, half the wave height. There's amplitude again, but the frequency, when we talk about frequency, we talk about how often something occurs. Okay, so we measure how quickly the wave passes by measuring how quickly the distance between one trough and the next, or one trough and the next, or one crest and the next, passes a certain point. Right, so if we move from one crest to the next crest in 1 second, then we say that that wavelength has a frequency of 1 cycle per second, or 1 wave per second. Okay, more importantly, how does the water move in a wave? Okay, this is the counterintuitive thing. Most of us have probably seen, again, either standing on the coast or on a boat, seen something floating in the water, right? A fishing bobber or a bird, garbage, any kind of floating object. When there's a decent set of waves coming through, it looks like that object is moving back and forth, back and forth, back and forth. Obviously, it's moving up and down because you can see it following the crests and the troughs of the waves. But the reason it looks like it's moving back and forth is because the particles. So once that energy is transferred from the wind up here, pushes on this water here, starts to pile up the water. So it's gaining enough energy to pile up that water. How are the water molecules actually moving? The water molecules transfer the water in a circular pattern. So the energy transfers here. The water passes energy from one water molecule to another water molecule to another water molecule, and it starts to follow this circular path like this. Okay, now while the waves look like they're rolling this way, while it looks like the water itself is moving this way, it actually is not. The water, or at least not to a large degree. The majority of the movement in the water molecules themselves are in this circular motion. Okay, so we can measure from crest to crest to get the wave height, right? But if we take half of that, or I'm sorry, the wavelength, if we take half that wavelength, that's usually how deep the energy goes. Okay, so really, for this wavelength, the energy of this water should have ended here, not here. And so this circular parcel of water, moving parcel of water, transfers some of its energy to parcels of water below it, which continue that circular motion, which transfer energy to parcels below that, and the depth that it reaches is only half the wave height. I'm sorry, half the wavelength. And as it goes deeper and deeper, the energy dissipates, right? So the main energy source, the full energy source, is the wind up here, and as they transfer energy here and here, it loses energy with heat and energy waste, and so the strength of that wave gets smaller and smaller. So if you can get below the half the wave length, then you get out of the wave action. Right? Movement reaches a depth at about half the wavelength and then stops. So that's what they say by getting beneath the waves. So the water movement is in this circular pattern. That's the water molecules, but the energy itself is moving this way. Okay? The energy is being dissipated and the water molecules are moving this way, but the energy from the wind, the causing winds, is moving in a linear direction in the direction of the wind. All right? So that's why waves do appear to be rolling in one direction, because the point origin of the energy is the wind, and some of that energy dissipates in the circular moving water, but the direction of the energy is in a linear fashion this way. Right? So remember, the water molecules themselves move in a circular pattern, but the energy dissipates in this linear motion this way. Where we see that dissipation, the ultimate dissipation, as we approach the beach. Right? The wavelength increases and wave height increases as the waves approach the shore. And why is that? Right? So we have a constant energy transfer from here to here, because the wave, half the wavelength, is how deep the wave goes, and here it's not touching anything, right? There's just water below it. But as we get into shallower water, the wave energy begins to touch the bottom, begins to touch the sea floor. And as it does that, we have a friction interaction, right? It starts interrupting with that transfer of energy. And we could think of that as our diagrams, in terms of our diagrams where flow, any kind of flow moving this way, energy flow moving this way, once it starts to interact with a surface, in this case a solid surface, the seafloor, it begins to interact with that surface and we get friction, which causes turbulence, and the waves actually drag against the bottom and then begin to trip over on themselves. And the result is that once the energy moving this way or once the drag overcomes the energy moving this way, then we get the waves crashing. Okay, so what are some other sources of waves? Okay, one other major one is storm surge, right? So the wind and the pressure from an atmospheric uh, um, disturbance, a major atmospheric disturbance, so not persistent or short-term winds that are natural, but a large weather system can cause what we call storm surge. So we should recognize this system as a hurricane, which is a low pressure center. And because the pressure is lower in the center than it is on the outside, it actually causes the water to bulge up. Okay, so there's a lot of wind in a hurricane, so that causes waves as it is on its own. But this differential in pressure causes this extra bulge here, which causes extra large waves. And as the waves it piles up directly below the system and is sent in the direction of the wind. Okay, another source that I want you to know about, and again, it's water displacement through disturbance of energy, but these are much more rare, but also a much higher magnitude wave, right? Some of the largest waves that we know of. We'll talk about what is the largest wave in the next lesson. But so we can have underground earthquakes. We can also have, underwater earthquakes, but which is underground, right? So these plate boundaries that we talked about in plate tectonics, when they move in a large way, and by a large way I mean possibly centimeters, right? Even if this seafloor all of a sudden gave way and rose up 5 centimeters, picture that pushing up in a quick instant, 4,000 meters of water all of a sudden rise up 5 centimeters. It creates a gigantic surge, a huge water displacement wave. Okay, and that's why earthquakes offshore can cause essentially a tsunami. All right. Another way that we get tsunamis are underwater landslides. So where the water meets the coasts, we have slopes, and they could be gentle or steep, but we have all this erosion from land, and all this dirt just piles up and piles up and piles up as it dumps out into the ocean, and then sometimes it becomes unstable, or it can get disturbed, and all of a sudden that sloughs off, and all that dirt just piles up and pushes water very quickly, and that can cause a very large wave to a smaller scale tsunami than an earthquake. And so that's really it, and all I want you to know for waves. We'll talk about the largest wave, which has an awful lot of different characteristics in these kinds of waves in the next lesson. Thank you.